chapter, we will deal with relations between force and acceleration. So we'll deal with kinetics of a particle. The objectives of this chapter is to know how to apply the Newton law in different type of coordinate systems. We have already developed in chapter 12 Cartesian coordinates, normal tangential coordinates, cylindrical coordinates. So what we will do now is, depending on the given, we'll decide which frame to use, and we will apply Newton law to relate forces to acceleration. And then from acceleration, we can get information about velocity, position. So to start with, we'll introduce in brief the main Newton's law that we'll use in this chapter. The second law of Newton is the most used relation in dynamics. So you have sum of forces for a particle. It's just sum of forces equal to the mass times acceleration of g. And we can decompose this vectorial relation into several equations. In Cartesian coordinates, we'll write it sum of x equals magx, sum of y equals magy, sum of z equals magz, okay? And in normal tangential coordinates, we'll decompose it into sum of normal forces, sum of tangential forces, and sum of forces along B. Now, concerning the Newton's law of gravitational attraction, this law will give us a force of attraction between any two particles. It states that if we have a particle of mass m1 and another particle of mass m2, and the distance between them is equal to r, the attractive force, the gravitational attraction between them, is given by a certain gravitational constant times m1, m2 over r squared. This equation in particular will give us the expression of the weight, because one application of this equation is when we consider one of the two bodies, the Earth, and the second body, any mass m. So we can say that the force of attraction between the Earth and the particle, which is equal to the weight, is equal to g times the mass of the Earth times the mass of the particle over the distance between the center of the Earth and the particle. So if this is the radius of the Earth and this is the height of the particle, then we can say that the force F is equal, the weight is equal to gmem over radius of Earth plus height of the particle or altitude of the particle squared. Now, in general, you use g equals 9.81. This is only valid if you are very close to the surface of the Earth, or if the altitude is much smaller compared to the radius of the Earth. So when we say g equal 9.81, this corresponds to the gravitational constant times the mass of the Earth over the radius of the Earth square. Now, higher the altitude is, lower will be g. Okay, so when h will increase a lot, g will decrease. And this is why for satellites, we say that if h is large enough, g can tend to 0. This is why we say that when we are very far from the Earth, the weight can be neglected. I will do with you a review for the exam after, and we'll do these problems, okay? But I prefer to do them together, so on campus. So now just we'll continue with a new chapter. So now concerning the Newton's law of gravitational attraction, as we said, one of its particular application is the calculation of weight. And for the case where the object is at the top of the Earth, then, or very close to the Earth, then G can be taken as 9.81. In case we have large altitudes, we have to apply the formula to get G. Now, whenever we have a problem, the first step to be able to solve it is to draw what we call a free body diagram. A free body diagram is a representation of all forces acting on a particle. And it will help us into determining what are our unknowns, what can we find from the analysis of forces. Now, we know from Newton's law that sum of forces is equal to ma. So we can replace, if you do summation of your forces, so for example here, if you have two forces acting on your particle, summing these two forces, you can do it analytically, you can do it geometrically. So if you sum these two vectors, you get the diagonal in the parallelogram. This is the resultant force. And from Newton's law, the resultant force is mass of the particle times its acceleration. So if we represent just vector ma, this is called the kinetic diagram. Okay. Now, in case sum of forces equal to 0, then no acceleration. And this is, if you want, it can be a static equilibrium or a dynamic equilibrium. Static equilibrium means no motion. Dynamic equilibrium means motion, but with constant velocity, without acceleration. So in this way, we'll be back to the first law of Newton, which you used in statics.
Doctor, I have a question.
Yes.
It's also, there's another component when m is changing, if the mass is changing, or we're not gonna deal with that?
Yeah, in these cases, we are considering constant mass, not variable mass. Okay, if the mass is changing, the general rule is that sum of forces is the derivative of mv with respect to time. Okay, and yes, as you said, then it should be, if m is varying, we should decompose this term into two parts, which are m dv by dt, which is m times a, plus dm by dt times v. Okay, but for our study here, for rigid bodies and for particles, we'll consider constant mass, no variable mass. This is why this term will cancel out, and sum of forces will be equal to mass times acceleration.
Okay. Thank you so
Okay.
much.
Okay. Now, what is an inertial reference frame? Any frame that is translating with respect to the fixed frame, to the absolute frame, okay, with no acceleration, is considered inertial. A non-inertial frame is a frame having a certain acceleration. Okay, so we say that acceleration of the particle is measured with respect to a reference frame that is either fixed or translates with a constant velocity. Such a frame of reference is known as Newtonian or inertial reference frame. Now, what will happen if we consider non-inertial reference frame? Yani, for example, if you have a car, okay, if you have a car moving at constant velocity, v constant, then if you have any particle accelerating, let's say, in the fixed frame, the acceleration of the particle measured here will be equal to the acceleration measured by the car. However, if you consider that the car is accelerating, then the acceleration you measure in the absolute frame will be different from the acceleration you measure in the car. And also we say that if we consider, for example, the car with a certain acceleration a, then when you are inside the car, you will feel a force that is called inertial force. What do we mean by this? So imagine that you are in the car and suddenly you put the brakes on. When you put the brakes on, your body will tend to move in this direction. Why? Because it will experience a force called inertia force that is opposing the deceleration of your car. So whenever you put the brakes on, you have A that is towards the left. Okay, so you have deceleration effect. To oppose this deceleration effect, your body will tend to move forward, because we say that whenever we are in a non-inertial frame, we experience an additional force, and we call it effective force. Why? Because if an occupant is observing from outside and he is measuring forces acting on this person, he will not measure the inertia force. Okay. However, for a person inside the car, it will experience this force, and this force is called inertia force and is equal to minus ma. So what you should know is, whenever I have a balance of forces that I treat in a fixed frame, and if I look at the occupant from outside, okay, and I want to determine what are the forces acting on it. So I have an occupant in the car. I say I have its weight, I have the normal, and I have, let's say, the chair of the chair is putting a force on it in this direction, so it can move with the car. These are the forces I can see in such a frame. Okay. However, if I consider the frame of the car, in addition to these forces, I will experience the inertial force. Okay. And if you do the analysis at the end, when you do the analysis in the inertial or non-inertial frame, you should obtain the same result as an equation. Why? Because let us say you are looking from outside. Okay. Then what is happening is you have a deceleration of your car. Under the effect of this deceleration, you will have so the acceleration that the man is measuring is this acceleration A. Okay. Now, if I write sum of forces, what are sum of forces? Sum of forces on the occupant for me equals to the force. This force, I will call it F chair. So F chair. And of course, you have, so here we said the normal and the weight will cancel out. Okay. You have the force of the chair acting on your occupant. And also you can have it, and this force can be, we put it in this direction, but it can be, depending on the situation, it can be like this or in the opposite direction. So you have the contact with the chair, you have also the contact here with the ground. So the ground also might do on you a certain force. I will not decompose these forces. I will call them like resultant force of the car. So let us call them Fr. So you have the resultant force of the car on you. Okay. This should be equal to the mass of the person, okay, times the acceleration of the person. Okay. So this is what you observe in with respect, if you want, to the absolute frame. Now, if you do the analysis with respect to the car, okay, you will feel, in addition to these forces, okay, you will feel the effect of inertia force. So the idea now is, with respect to the car, you are not moving. You are a sitting occupant, okay? You are not moving with respect to the car. But this is why in the car system, since you are fixed, sum of forces on the person in the car, so is equal to 0. Because I'm not moving with respect to the car, I'm moving with respect to an occupant looking from outside. Okay. But when I write sum of forces here, what should I add? I should add the inertia force. Okay. I should add the inertia force to these forces. So I will get that F resultant minus mass of the person Now, since if you want the person is fixed relative to the car, then they should have both same acceleration. So it's minus mp times acceleration of the car, which is the same as acceleration of the person, equals to 0. So in this case, nothing will change, because if you take this term to the other side, you will get exactly the same result. Okay, so the idea is whatever is the frame you are working in, inertial or non-inertial, you will get the same result. But the difference is that when you are working Newton law in a fixed frame or inertial frame, then you should not consider the inertia force. However, when you write the Newton law within a non-inertial frame, you should add the effect of inertia force, and both will lead at the end to the same result. Okay, any question on this? In general, in this course, we'll work with inertial frames. Now, what is the equation of motion in a certain whenever we talk in an absolute frame? Okay, the equation of motion is sum of external forces equals to ma. Now, in case the frame is non-inertial, we should add, if you want, the inertia force to the balance of forces. This is the only difference. So if we consider then the case of sum of forces equal ma, we have the following. If we have one particle, we can take all forces acting on it and say that sum of forces is equal to 0. Okay. Now, in case or if it's at rest, its sum of forces equal to 0, or if its velocity is constant, it's equal to 0. If it has a certain acceleration a, we write on it sum of forces equals ma. This is for one particle. Now, what if we have several particles? What should we do? If we have several particles, then what we should do is we should consider each particle, consider what are the forces acting on each of our particles. And of course, whenever you have a system of particles, you have interaction between particles. So I will put them in another color. You have external forces and you have interaction between particles of your systems. But since by action reaction, always any two particles in your system will have opposite action reaction between them. So this is the concept. This is the third law of Newton. The third law of Newton states that whenever you have two bodies, they can be in contact or they can have attraction force at distance. If they are in contact, any two bodies in contact will have, if this is A and this is B, you have that the force of A and B on B is equal and opposite to the force of B on A, irrespective of the size and the mass of the objects. Okay, so this is the interactive law, action reaction between any two bodies. The two bodies can be in contact or can be at a certain distance. So here you have for example, in this case, you have attraction, mutual attraction between the particles, and the forces are opposing each other's. So now when you do the summation of all forces acting on your particles, the red forces, which are attractive forces between your particles, will cancel out. We call them internal forces to the system. So you will only be left with the forces in green, which are external forces on the particles. This is why we say that because always by action reaction, the internal forces summation will cancel out, then this term will drop out. And we can say that sum of external forces is equal to summation of MIAI. where mi is the mass of individual particles and ai is the acceleration of each of these particles. Now, we can demonstrate, okay, that we can write also sum of forces equal to sum of elementary mass times acceleration of each particle. Because you know that whenever we consider a certain system, as we have seen now, the internal force cancel out, and for each particle, it can have a different acceleration from the other. Now, how we can replace this term? We'll demonstrate together that we can replace sum of elementary mass times acceleration of each mass by the total mass times acceleration of the center of mass G. What is the definition of a center of mass? You know that the center of mass in general is used to replace several particles. So if I have several particles and I want to replace them by just one point, okay, for this point to be representative of all of these particles, if I take a certain frame and I want to detect the position of G, which is the center of mass, I say that vector OG, okay, should be in a way that the total mass times vector OG is equal to summation of mass of each particle times its corresponding position vector. Okay, so in this way, because I'm multiplying RG by the total mass in a way that MRG is equal to summation of MIRI, then G can be a representative point of my whole system. Now, this is the formula of the center of mass. According to this formula, if I derive the first time with respect to time, I get mass, total mass, times velocity of G equals to summation of mass, each mass times its own velocity. And if I derive another time, I get that the total mass times acceleration of G is equal to summation of MIAI. So I can deduce then that I can replace, whenever I have a system, I can replace some of external forces acting on it by the total mass times acceleration of the center of mass of the system. Now, let us start to see how to apply this law in practice. Okay, so we'll start with application of Newton law in rectangular coordinates. So as we said, this is a vectorial relation, and any vectorial relation can be decomposed into algebraic equations depending on the frame you are working in. So if you are working in XYZ frame, this vectorial relation can be decomposed into sum of x equals max, sum of y equals may, and sum of z equals to maz. Okay. Now, let us consider forces acting on a particle. We should draw the free body diagram of it. And then once we draw the free body diagram, we can decompose forces into x, y, and z. So we end up with 3 equations. So we can solve up to 3 unknowns. So whenever you have any problem, let's say 3 forces unknowns, and you know your acceleration, you can find the component of your forces. Sometimes if you don't know acceleration, you can use these relations to get the acceleration. So we can vary the problem input and always, to be able to solve just by these 3 equations, we should only have 3 unknowns. If we have more than 3 unknowns, we should look at an additional relation. Sometimes you can get it geometrically. Sometimes you can get it, for example, from relation. Let's say you have a spring you have that tension in the spring is equal to K delta L. So you can relate the spring stretching to the tension developed. So if you have more than 4 unknowns, you need an additional relation to close your system. Now we'll start to do some applications on Newton law. Let us consider this simple problem in order to see how we can use Newton law in rectangular coordinates. So first, we have a 50-kilogram crate that rests on a horizontal plane for which the coefficient of kinetic friction is given by mu k equals to 0.3. Before starting this problem, I want to introduce the concept of friction. Whenever we talk about friction, you have two types of friction, kinetic friction and static friction. What is the difference? Let us take this example to understand the difference between the two. I will give you in this problem, in addition to mu k, also mu s. Mu s is called the static friction coefficient. And this static friction coefficient is always larger than mu k. So for example, here, let us take it as 0.5. And what is the idea of this coefficient? If you have a box in contact with a rough surface, not any force, not any horizontal force applied on the box will be able to move the box, because you know that a rough surface will develop a certain friction force to oppose motion of your block. Now, this friction force can be of two types, static and kinetic. Whenever we say we have a static friction, this means that no sliding between the surfaces. Okay, so as long as you have a static friction, the two surfaces will not slide with respect to each other. And in the case of a box that is sitting on the ground, if it's not sliding with respect to the ground, which is fixed, then the box will be fixed. So
then we'll use sum of forces equals to 0, right?
Yes, exactly. Then we use sum of forces equal to 0. Because in this case, we know that the ground is fixed. And since no sliding between the ground and the box, then we can say that the box is at rest. Okay? Now, what is the condition to maintain this equilibrium? F static has a limit. It cannot take any value. We have a formula saying that the maximum value of F static is mu s times the normal force between the ground and the box. Okay, so this is the maximum possible static friction. It can be smaller than this, but it cannot be larger. What do we mean? How we can use this information? For example, if you take this problem, if I have a 50-kilogram crate, I will put here P, I will call it P horizontal, okay? A 50-kilogram crate means that the weight is, so let us illustrate all forces. The weight is 500. I will take G10. And because in the example here I gave you, I just have a horizontal component of the force, no vertical component like this figure. So just the normal here, N, will be equal to the weight. So N is equal to 500, let's say. Okay. Now, since F is smaller or equal to mu Sn, then I can say that F will be smaller or equal to 0.5 times 500, which is 250. This means what? This means that if I apply a force P horizontal smaller than 250, then I will not attain the maximum static friction, because as you can see here, what are the forces acting on your system? P horizontal in the horizontal direction, P horizontal and the static friction. Okay, so I say let me assume equilibrium condition. If I have equilibrium condition, the static friction should be just equal to pH. So as long as P horizontal is smaller than 250, then my static friction will not exceed 250 and equilibrium will be maintained. When I just exceed 250, and if I put 250 point something, then my static friction cannot anymore ensure equilibrium because it has reached its maximum limit. So whenever I just exceed 250, my box will move because my friction is not able anymore to oppose motion. And then I will have motion. And at this instant, the static friction will drop from static value to kinetic value. And the kinetic value of friction is F kinetic equals to mu K times N. So when I just exceed 250, the friction will become kinetic. And it will be equal then to 0.3 times 500 equals to 150. And then my box will have a certain acceleration and will move. Okay, so this is the idea between what is the difference between static and kinetic. Now, in some problems, they don't tell you if the box is moving or not. They give you both coefficients, and it's up to you to determine if it will move or not. Let us try to do it in the example here. In the example here, since they just gave us the kinetic friction, so we understand that it's moving. But in case they didn't tell us it's moving, and they gave us that mu k is 0.3, and mu s, let's say, is, for example, 0.4, and we want to determine if it will move or not, what we should do is first we'll put the balance of forces. So we say that we have here the normal, we have the weight, and we have the friction, but we don't know if it's static or kinetic. Whenever we don't know if it's static or kinetic, we should do an assumption. And always we start by the assumption of static case. I will tell you what. So you start by saying, let us assume that we have a static friction. If we have a static friction, as you said before, no sliding between surfaces, and the ground is fixed, so the box is fixed also. So sum of forces will be equal to 0. And sum of forces as a vector is equal to 0. And now I decompose it into x and y. Along y direction, so first let me write it along y. What do I get? Sum of y equals to 0. I have plus normal minus weight, and P should be decomposed into two components, one in the vertical direction, one in the horizontal direction. The vertical component of P is plus 400 sine 30 equals to 0. So I have that the normal is equal to the weight, which is 500, minus 400 sine 30, which is 200. So minus 200 equals to 300. Okay. Now, once I get the normal from sum of y equals 0, I can move to my second equation. Okay. My second equation is sum of x equals to 0. Along x, the forces are the projection of P, which is 400 cosine 30, and this is my friction, and I assume here it's static, okay, minus F static equals 0. What do I get? I get that F static should be equal to 400 cosine 30. But when I am done with my calculation, I cannot stop here. I should verify my assumption. My assumption was that I have a static friction, and I know that the static friction should be smaller or equal to mu Sn. So let us verify if Fs is smaller than mu Sn. If you calculate mu Sn here, it's equal to 0.4 times 300, which is equal to 120. Okay, and 120 is much smaller than 400 cosine 30. So because this is larger than 120 Newton, I say, which is mu Sn, I say this is wrong. My assumption is wrong. So I cannot have a static case here. My box is moving. And once I determine that my box is moving, then I can directly say the friction here is not static. The friction is kinetic. Okay, and then I will repeat my calculations based on sum of forces equal MA. I don't have any more equilibrium conditions. So here, because they didn't give me the two coefficients, static and kinetic, then I am sure that it's moving. And already they told us to determine the velocity after 3 seconds. So of course it's moving, but it's important to know this concept because we'll use it a lot after in problems. Okay, so here I know that my box is moving, so the friction is a kinetic friction, and it equals mu Kn. We already calculated the value of n, and we have mu k equals to 0.3. So we have 0.3 times the normal was equal to 300. So times 300. You get the normal from sum of y equals to 0. So this is equal to 90. And now, once we obtain the value of the kinetic friction, in order to solve for the acceleration, why we need the acceleration? They told us determine the velocity after 3 seconds. You know that velocity is related to acceleration and time. So if whenever you have such a problem, you know forces are acting on your system, and you want to get information about velocity, think about combining the two chapters, 12 and 13. So as a first step, I should find my acceleration by applying Newton's law. And once I find my acceleration from Newton's law, I can move back to the previous chapter to relate acceleration to velocity. Okay? So here, next step will be to determine what is AX. The motion here is only in X direction. So when I get AX, and I can integrate it to get V and to solve for my velocity after 3 seconds. Okay, now to get AX, what should I do? I should apply Newton's law along the direction of motion. So I just have to write sum of x equals to MAX. And now if I project forces along AX, I have two forces along AX. The projection of P, which is P cosine 30, and my